Okay, so get it out of your system, people. Say hello to Luke if you need to. Okay, so the very last thing we need to look at is a type of energy that I brushed over in the beginning. When we think about types of energy, or you're asked questions about types of energy, you should be thinking mechanical. There's some specific questions versus non-mechanical. And basically when the non-mechanical comes in, we're talking usually about heat, thermodynamic kind of stuff. Mechanical, we have to look at KE, we have to look at PE. In KE, we've looked at KE initial so far, and KE final. In PE, we've looked at PEG, potential energy due to gravitation, which has to do with height. And today we're going to look at what's called PEE, which is equal to potential energy elastic, or it's actually called elastic potential energy. And it is the last type of energy that we're going to look at any math with. This would be called sometimes PE type 2. If you have a text that refers to type 1 and type 2, type 1 is always gravitational, type 2 is always elastic. This is stored energy of a compressed object. And usually the compressed object, when they talk about it, even though there are lots of different things it can be applied to, most commonly it's a spring that we're looking at. You might use it in a lab with a rubber band, or in a situation with something like maybe a bungee cord. Think about when you were a little kid, you probably had one of those popper toys, like you push it down and it would jump. That's elastic potential energy. That's due to a spring. Your ink pen, like I'm looking at Gavin's right now, I don't know if it's a pencil. Nope, that's a pencil. Never mind. It should have a little spring in it, though, that lets you make it either on or off. So that's more elastic potential energy that's stored. So those all could be used as examples. When I think about this, I can say the length when no force is acting on the object will be called in a problem the relaxed length. And anytime I have any kind of squish, it'll be called compressed length. Then I can also have the stretch, which would be stretched length. So you have to read these problems a little bit carefully and pay attention, because lots of times the distance you're actually using is the difference between the compressed and the stretched, or the at rest versus the compressed. You just have to really analyze what they're telling you is happening. Obviously, when we talk about these things, the PE elastic is stored in the spring or whatever system you're talking about. Think about the spring scales we've used. We used them to get the mass of your cars. You know, when it's just there, my spring is compressed. Depending upon how heavy your car was, it stretched the spring. So it worked against the elastic potential energy. The amount of energy depends on the distance, the spring, is compressed or stretched from original length. So how much energy is there depends on how much I stretch it or how much I squish it. The formula looks like this. PE elastic equals 1/2 kx squared. Where K is called the spring constant. It's like the toughness or the difficulty of stretching something. What? It is, yes. It is measured in newtons per meter, so it's force per meter, or force per unit. This X, we've seen before, this is your displacement. The amount of stretch or squish. And it is measured in meters. So if you're keeping a card still, put that one on your card. This is also known as Hooke's Law. Hooke's the guy that figured it out. He did lots of experimentation with springs. Now I want you to think about this K for a minute, which is my spring constant. And we're going to think about it in two ways. If my K is a small number, versus a large number. Now think about that for just a minute. If I have a small spring constant, do I have a strong spring or a weak spring? What? Why? Because there's less tension. That tells me it's easier to stretch, right? This would be easy to stretch. Or I'm just going to put the word weak right here. Give me an example of a weak, something that would have a weak spring constant. Maybe. That's a possibility. What? Materials, yeah. Like, what about the spring in your pencil? That's pretty weak. How many of you have taken an ink pen apart before? Have you played with the spring in Sky? It's pretty easy to deform, right? So it would have a very low spring constant. Now think about this. What is the strongest spring you can think of? Oh, that's a good one. I got another one. There are. Have you ever been to the mall at Fairfield Commons? Yeah, if you stand really still, sometimes you can feel it moving. There's some suspension, some spring system in that building. How many of you have a trampoline at home? Oh man, people, you need a trampoline. How about the springs on the trampoline? Those are pretty hard to stretch. They would have a high spring constant. So this tells me hard to stretch. Something that's very strong, has a high spring constant. The car's better than the trampoline, though, I have to say. I didn't think about that one this morning. I was just thinking about the trampoline because I pinched my finger in one of those before. So I know it's a strong spring. All right, grab the handout I had you pick up. Gotta find one. We're just going to look at the example problem. And what I've done on this, I think these problems are pretty easy. They're pretty straightforward. I mixed in some gravitational potential energy and a couple other things on this last handout. It's the last thing you'll get besides the review, which I'll have for you tomorrow. We are not going to test until Monday and Tuesday because it's too much to try to get done, all the review, in one day. So we're gonna do multiple choice short answer on Monday, problems on Tuesday, because it takes me longer to grade the short answer, so that'll give me an extra day. So let's look at example 1. A spring force has a constant of 500 newtons per meter. Show the energy stored in the spring as followed. So, PE elastic equals 1/2 K x squared. I didn't leave myself enough room. So all we're doing is proving the formula works. A is telling me that when it's stretched 4 centimeters from equilibrium, so my x would be 0.04 meters. My K is what I was given, 500.0 Newton meters. So I'm going to go PE elastic equals 1/2 500 Newton meters times 0.04 meters squared, and I'm going to get an answer. Hopefully it equals whatever I said it was supposed to. 0.400 joules. See if that's right. Did I pick the right numbers? That's all you're doing. You're just plugging away with the formula. 0.5 times 500. Yay. I was a little worried. Yes, it does equal it. So you just proved it. That's all you're doing in B and C. I'm not going to work those. So what you're going to do today is, I got to find a copy of it. Handout 3, I'm going to have you, these are the ones I want you to do in class today. I want you to get done for sure. I want you to get 1 done, 2 done. Remember, 2 is where I have to use the sign of the angle. 1, 2, and then 1, 2, 4. So number 3 is the real long one with A through E. Skip over that one today.
So, do you want us to skip 1 and 2 on power too?
No, I just said do 1, 2, 4.
Oh, okay.
You're skipping 3. You're not doing number 3 in power. You're not doing number 3 on the first section. That's all. That's an easier way to say it, probably. So you may work in lab groups. Call me to check answers. Call me to help you set things up if you need help.
Can you check this?
Sure.
Oh, and also on A on that, why did you say don't do A? Because don't you need A to find
You do. You do. And I didn't realize that till
Okay.
you do the key.
I did it anyway because I was like, you
You
need
use
this.
cosine. And because it's a weight, you have to use sine. Because it's a downward force that's causing it
What was that one?
on A.
Okay.
So it's going to make your answers off. So, but I can tell by checking this. There we go. No.
Wait, what, the first answer, number 1, did you get 67.9?
Yes, that is correct. On power?
Yeah.
Yes, that's right. So what do we got here? Oh. And you didn't do anything with this. So we have, let me grab a pencil. So when we're looking at our forces, we have this, the mass of the elevator, and the mass of the load. Right? So I have to do
Yeah,
my,
that's the maximum. Right.
it carries a maximum load of.
Yeah.
So that means
Is
you
it-
need
is
to
it
add
carrying
those
the
two.
load?
It
Or
says,
it just says it can.
it says carries a maximum load. That's telling
So
you
it
it's
is
full.
carrying.
Yes.
Oh.
Plus, this is the one I talked about where you have to add the friction because the machine has to overcome the friction.
I did that part.
So did you do that?
Yeah.
I got negative on 1.
Okay. And that's irrelevant, so. So you're gonna have to fix that with your 800, which then changes everything.
What did you use for
And
the?
this one, number 2, good. Okay, that's right, okay.
Yeah, okay, sorry.
That one is off, what do we do? I don't remember that number. to be times sine of 20 because of the driveway, going up and
Yeah.
down the driveway. And then, oh, wait a minute. Okay. And then we have to subtract our friction, which you did.
Yeah.
Minus 4 times 10 to the third, so that's good. And then you multiply by that. You don't need that there.
Okay.
Okay, so I'll let you fix that. So you were almost right, yes. No, remember, oh, I don't need to check that. Hey, good job, that's right. That's right, that's right. Good job, Carter.
Those are the only two I have.
It shouldn't be negative.
I thought that since we used cosine, it should come out negative.
Your velocity won't come out negative.
Okay.
Your net work may come out negative, depending upon, oh, I see what we did here. So here, in this one, I talked about this yesterday. Oh, wait a minute, maybe this is, nope, you're okay, I'm not on the right problem. This one, F net sine D, which are F net. Okay, no. So we have to do, when we do this, we have to do, use sine, we have to do F, D, sine, beta, and my force was I have to do the 2 times 10 to the third kilograms times my 9.81, whoops, 1 times my sine of 20, because that's what's actually the weight of the object. It's going up the
Okay.
hill.
And then do you multiply by
Then
sine
I would
again?
multiply it times 4, or I would subtract 4 times 10 to the third, because that's my force in, that's my FK.
Okay.
Okay, and then I have to multiply by my 5, was it 5 meters? Yeah, 5 meters. Then it's my distance. So this is finding my F net
Okay.
first, and then I can't multiply until I find my F net. So you have things almost set up right. Then once you get that, you can set equal to 1/2 the 2,000 VF squared, which is what you have right there, which is correct. But it's going to change this answer.
Okay.
Okay?
Alright.
Jace, did I just answer your question?
Yeah, I think I figured out
Okay. Keaton, what you doing? You done? What are you doing, Preston?
Pull up the notes from last week.
Oh my goodness. I've been recording all this time. Sorry, Luke, we were done a long time ago.